On the 31st of May 2013, central Oklahoma felt like a powder keg waiting to explode. The air was heavy, thick with humidity, and unnaturally warm. Just 11 days earlier, an EF5 tornado had ravaged the town of Moore, leaving behind a trail of crumpled homes and shattered lives. But now, near the small city of El Reno, the atmosphere was recharging. Meteorologists watched their screens with growing unease. The convective available potential energy, CAPE, a measurement of atmospheric instability, had climbed to an astonishing 6,000 joules per kilogram. For context, a normal severe weather day might see 2,000 or 3,000. This was off the charts. A cold front was pushing down from the northwest, while a dry line crept in from the west. Where they met, at a point called the Triple Point, the air had no choice but to rocket upward. Above it all sat a cap, a warm layer that acts like a lid on a boiling pot. When that lid blew off at 4:30 p.m., the explosion was violent. Thunderstorm towers shot to 15,000 meters in just 16 minutes. A supercell was born. At 6:03 p.m., a small dusty whirl appeared under a brooding wall cloud southwest of El Reno. To anyone watching, it looked harmless, the kind of twister you could easily avoid. But radar data from Dr. Jana Hauser and Dr. Howard Bluestein told a terrifyingly different story. Their mobile radar, which scanned the storm every 2 seconds, revealed something that defied meteorological textbooks. Strong rotation already existed at ground level before it appeared in the clouds. This tornado was not descending from the sky, it was building upward from the earth. Within minutes, the storm began to metastasize. What had been a slender rope expanded with horrifying speed. By 6:19 p.m., when the tornado crossed US Highway 81, it no longer looked like a funnel at all. The cloud base had dropped so low that the entire rotating wall cloud had become the tornado. It was now a wedge wider than it was tall. At its peak, radar measurements confirmed the tornadic winds stretched an almost incomprehensible 4.2 kilometers, 2.6 miles, across. That is roughly the width of Manhattan Island. Imagine a spinning vortex of 500 kilometers per hour winds spanning from the Hudson River to the East River, grinding everything in between. But width was only half the nightmare. Inside this massive circulation, something even more frightening was happening. The El Reno tornado had become a multiple vortex tornado. It was no longer one spinning column of air, but a spinning wheel of smaller, more intense tornadoes rotating around a common center. Each of these sub-vortices behaved like a figure skater, pulling in arms smaller and faster. Mobile Doppler radars captured wind speeds of 476 to 503 kilometers per hour, 296 to 313 miles per hour. That is just shy of the strongest wind ever measured on Earth. And the motion of these sub-vortices was pure madness. While the main tornado lumbered east at 50 to 65 kilometers per hour, the sub-vortices on the southern edge would suddenly swing outward and shoot forward at nearly 290 kilometers per hour. On the northern side, they would loop backward, almost standing still. This trochoidal motion made the tornado impossibly unpredictable. As if that were not enough, a separate satellite tornado formed to the southeast. It was anticyclonic, spinning clockwise, the opposite of normal and powerful enough to be a monster on its own. For 15 minutes, 2 massive tornadoes danced across Oklahoma farmland, one cyclonic and one anticyclonic, in a grim and chaotic ballet. Driving directly toward this chaos was Tim Samaras, one of the most respected storm chasers in the world. Tim was no thrill-seeker. He was an engineer, a meticulous researcher who had designed hardened probes called turtles to place directly in tornado paths. His goal was to measure near-surface wind pressure data that could help build stronger homes and save lives. With him in his white Chevrolet Cobalt were his 2 4-year-old son, Paul, a videographer, and Carl Young, a 5-year-old meteorologist and longtime partner. They had originally planned to chase further north, but the potential of the El Reno storm was too great to ignore. At approximately 6:20 p.m., they drove east on Reuter Road, a gravel path running parallel to the tornado. Another chaser, Dan Robinson, was just ahead of them in a Toyota Yaris. From behind, Robinson's dashcam showed the headlights of the VORTEX vehicle following calmly through the rain. But the storm was changing faster than anyone realized. The tornado had expanded so rapidly that they were no longer driving beside it. They were driving straight into its outer edge. The rain-free area they assumed was safe was actually the inflow jet, the feeding mouth of the vortex. Then the tornado turned. Instead of continuing southeast, it hooked sharply north and curled back. The southern flank surged outward. Dan Robinson escaped on foot, fleeing his car and pushing through the storm. But the VORTEX team was only 20 seconds behind him. Those 20 seconds were the difference between life and death. As the Cobalt reached the intersection of Reuter Road and Radio Road, a violent sub-vortex winds approaching 320 km per hour swallowed the vehicle whole. The 1.3-ton car was lifted and thrown nearly 800 meters through the air. When the wreckage was found, it was unrecognizable. Tim, Paul and Carl were killed instantly. It was the first time in history that storm chasers had been killed by a tornado. The shockwave through the meteorological community is still felt today. If Tim Samaras, the safest, most cautious chaser in the business, could be caught, then no one was safe. 8 people died that day. All of them were inside vehicles. The El Reno tornado forced a painful question. How do you rate a storm like this? The enhanced Fujita scale is based on ground damage, not wind speed. Because the tornado mostly crossed open fields and wheat farms, it only produced EF3, level destruction. But mobile radars had measured EF5 winds over 500 km per hour. Initially, the National Weather Service upgraded El Reno to EF5, a landmark decision that acknowledged technology could now see the wind even when it did not hit a house. But months later, they reversed the decision. The official record books list the widest and possibly strongest tornado in history as merely an EF3. Critics argue this is not just a technicality but a dangerous policy. If we ignore radar data, we underbuild critical infrastructure. We tell the public that 500 km per hour winds do not exist here because no house was standing to prove it. To the scientists who measured it and to the families of those lost, there is no doubt El Reno was an EF5. Tim Samaras and his team did not die in vain. Their data and the data collected by radar teams around them has advanced our understanding of tornado genesis more than decades of theory. We now know tornadoes can form from the ground up. We know they can expand to unimaginable widths in seconds. We know sub-vortices can move like race cars. They stared into the abyss so that others would not have to. And because of them, we watch the sky with a little more caution, a little more respect, and a profound awareness that some monsters hide in plain sight.